All right, let's dive right into this explainer. Today, we're going to demystify motor controls, and we're building them up from the absolute ground level. We'll start with your basic everyday switches and work our way up to the heavy hitters, those complex, smart variable frequency drives. Look, whether you're out there troubleshooting a massive industrial HVAC system or you just kind of want to know how the invisible logic of our mechanical world actually works, getting a grip on these concepts is absolutely crucial.
So here's our roadmap for today. Part 1, relays and contactors. Part 2, protecting motors from failure. And finally, Part 3, variable frequency drives. Let's get right to it.
Section 1, relays and contactors. All right, so these are the fundamental building blocks of electrical logic. Without them, we'd literally have humans standing around manually throwing giant levers to turn motors on, which is just not going to happen. But before we look at the hardware, we really need to nail down two baseline concepts, normally open and normally closed. Think of a circuit like a drawbridge. Normally open, or NO, means the bridge is up. The path is broken, right? So electricity cannot flow until that switch gets energized. On the flip side, normally closed, or NC, means the bridge is down. Electricity flows totally freely right up until the exact moment you energize the switch to break that circuit. And just a quick side note, in the motor control world, the normal state always refers to the device when it is completely de-energized, just sitting right there in the box. And you can really see this concept in action as the states change. Notice how the magnetic coil physically pulls those contacts to change their position when it gets energized. It's actually super clever. We've got this control circuit with a tiny coil, right? When current hits that coil, boom, it becomes an electromagnet. That magnetic field pulls on an armature attached to a little spring. Suddenly, those normally open contacts snap shut, and the normally closed ones pull apart. It's just this brilliantly simple mechanical way to control power indirectly.
Now, you really got to understand the massive difference between light-duty relays and heavy-duty contactors. On the light-duty side, we have your basic relay acting almost like a polite little traffic cop for small signals. We call this pilot duty. They're great for passing a low-voltage signal to a thermostat or maybe triggering an alarm, but they simply cannot handle the massive surge of juice a large motor pulls. They'd fry. That's exactly where heavy-duty contactors step in. These guys do the real heavy lifting. Their contacts are specially beefed up to handle incredibly high current without melting into a puddle, which means they have to have very, very low electrical resistance. They are, for sure, the true muscle of the whole operation. Okay, moving on to Section 2, protecting motors from failure. So, stepping at the hierarchy here, we have to introduce a little conflict into our electrical story. The harsh reality is motors fail, and man, they are incredibly expensive to replace. So they need a bodyguard, basically. Out in the field, they are facing constant threats. You've got dangerous single-phasing, which happens when a three-phase motor loses power on just one line, forcing the other two to work insanely hard and overheat. Then you've got locked rotors. That's when a motor physically cannot spin, but it's still trying with everything it has, pulling something like 3 to 5 times its normal current. Add in general overloads or just crazy hot ambient temperatures, and these are the primary culprits threatening expensive machinery every single day. Now, if you take away one specific number from this, it has to be 10%, plus or minus 10%. Motors are strictly engineered to operate within just 10% of their nameplate voltage. Go outside that, you're asking for serious damage. Let's say you've got a 460-volt motor. If you push it past that 10% tolerance, either too high or too low, you get this immediate, massive spike in heat. And heat is the absolute worst enemy of a motor's internal winding insulation. If you've ever wondered why facilities are so obsessed with monitoring their power quality, well, this is exactly why. So how do we actually protect against those failures? Well, we take our heavy-duty switch, that contactor we just talked about, and we pair it up with a protective bodyguard. This gives us what I like to call the golden equation for a motor starter. Starter equals contactor plus overload protection. It's that simple. The contactor gives us the brute force on and off muscle, and the overload device provides the brains, instantly killing the power if that motor starts pulling too much current and getting too hot. And looking at the hardware, there are two really distinct ways to get that overload protection. On one hand, you've got the modern, highly precise solid-state overload. This thing takes the motor current, turns it into an electronic signal, and gives you extreme accuracy. Plus, it runs super cool. On the other hand, you have the classic magnetic current overload. The big advantage here is that it reacts entirely based on a magnetic field, pulling a core inside a fluid-filled tube. Why does that matter? Because it's practically immune to the surrounding room temperature. That means it won't give you annoying nuisance trips just because it happens to be a sweltering hot summer day in the mechanical room. Now, when these devices actually step in and trip to save the motor, they have to be reset. They either reset automatically once everything is safe again, or they require a manual reset. You might be thinking, well, automatic is obviously better, right? Just let it cool down and start back up. But actually, manual reset has a massive operational advantage. It literally forces a technician to walk right up to the machine, physically push a reset button, and most importantly, investigate what went wrong in the first place. Think about it. If a motor keeps tripping and overload, there's a hidden problem somewhere. A manual reset makes sure that problem doesn't just get ignored until the motor finally burns itself out completely. All right, let's hit into our final part, Section 3, Variable Frequency Drives. This is where we evolve from those basic binary on or off starters into a realm of ultimate precision. We're talking about the true brain of modern motor control, the variable frequency drive, or VFD. Now, I know these things seem incredibly complex from the outside, but a VFD actually operates in just 3 totally logical steps. First, it grabs that incoming fixed frequency AC power right from the grid and runs it through a rectifier, turning it into DC power. Next, step 2, it takes that DC power and pushes it through a DC bus filter. This uses capacitors and inductors to smooth everything out into a nice, flat, steady DC voltage. Finally, step 3, it shoots that clean DC power into an inverter, which morphs it back into a highly controllable, adjustable frequency AC output. And by simply tweaking that frequency, we can dictate the exact rotational speed of the motor. It helps to think of the VFD as this master symphony conductor. See, it doesn't actually spit out a perfectly smooth, true AC sine wave like you'd get straight from the power company. No, it fakes it. It simulates a smooth sine wave by chopping up that DC power into these incredibly rapid pulses of varying widths. We call this a quasi-sinusoidal AC wave. But here's the crazy part. To the motor, the average of all those rapid positive and negative pulses feels exactly like a smooth, continuous wave. It just happily spins along at whatever speed the drive tells it to.
So how exactly is it pulling off this illusion? That rapid chopping technique is called pulse width modulation, or PWM. By constantly, dynamically changing how wide those electrical pulses are, it perfectly mimics the rise and fall of a natural AC wave. And the real MVPs making this magic happen, those are the IGBTs, insulated gate bipolar transistors. These little high-speed electronic components are the absolute workhorses inside the VFD. In what is honestly a total marvel of engineering, they operate in nanoseconds. They're switching massive, dangerous voltages on and off up to 15,000 times a second just to sculpt that simulated wave perfectly. It's wild. As we wrap up this explainer, I really want to leave you with a thought to ponder. See, because VFDs let us ramp motors up nice and slow and run them at the exact speed needed for a specific job, instead of just blasting them at 100% capacity all day, every day, they pay for themselves incredibly fast through just massive energy savings. So here's the question. As electronics keep getting cheaper and as global energy efficiency becomes absolutely paramount for all of us, is the humble old-school mechanical contactor eventually going to be completely wiped out by the smart VFD? It's a huge, fundamental shift in how we approach motor controls. But honestly, understanding both the old-school mechanics and the new-school electronics is the only real way to master this field. Keep exploring this stuff, guys, and thanks so much for joining me today.